So everyone ready? Okay, go on, Carlos.
Good, thank you. Okay, we are here for the thesis defense of the student Vitor Giudice Batista de Araújo Porto in the program, in the master program of electronical engineering and computing in the Technological Institute of Aeronautics, our ITA. The title of the thesis is Imitation Learning of a Model Predictive Controller for Real-Time Humanoid Robot Walking. In the committee, the examining committee, we have invited external members, Dr. Nicola Cianca from the Sapienza University of Rome, and Dr. Olivier Lee from the University of Bordeaux. Internal member, we have, I think only me, it's, my name is Carlos Henrique Foster. I'm from the Division of Computer Science in ITA. The advisors of the thesis are Marcos Ricardo Mena de Albuquerque Máximo and Rubens Junqueira Magalhães Afonso. One is from the computing from ITA, and Rubens is from electrical engineer in ITA. The defense is in our way to have the defense. Vitor will present 50 minutes his work. After that, the external members will have about 20 minutes each one to expose his questions and comments on the work. And after that, yes, also the internal members and the advisors. And finally, it's an open presentation, so people from the public can also make questions from the audience, can make questions and comments. I think we're good to go. I forgot something, Marcos, or no?
No, I think that may be something that may be confusing for them is because I told them that they have up to 50 minutes to talk. This is what's written in the document from the dean. So yeah, maybe you can clarify about that.
Number 20 is okay. Yeah?
Oh, 20 is okay. Okay.
50 that's
Okay.
a lot. I don't know.
Yeah, you told me that.
Yeah,
Okay,
we can use more. We can use more time. It's not a problem.
Okay, good.
Not a problem.
That's fine.
Good. So can start, Vitor.
Okay, can I share my screen? I'll share. Okay. Everyone can see clearly here?
Yes.
Yes.
Okay, just adjust the screen size. Just a second. Okay, I think now we're good to go. Okay, so hello everyone. As presented, my name is Vitor Giudice. I'll be presented my dissertation defense titled Imitation Learning of a Model Predictive Controller for Real-Time Humanoid Robot Walking. This is the final part of my master's under the supervision of Marcos Máximo and Professor Rubens Afonso of the Aeronautical Institute of Technology, also known as ITA of Brazil. So the outline of this work is going to be as follows. First, to do a brief introduction on the subject, highlighting the motivation for this work and the objective. Then I'll go over the dynamics of legged robots, more specifically biped humanoid robots, and the stability. Then I'll go over the theoretical background on imitation learning and its use for this particular problem. Then I'll do a literature review highlighting the state-of-the-art pieces of research that have been conducted on the field of robotics and imitation learning. And then we go over the methodology used to develop this work and the results obtained from this methodology. Finally, we draw conclusions and present possible future lines of work. So I just want to start by saying that humanoid robot walking, the problem of teaching a humanoid robot walk is of substantial importance to the field of robotics. Integrating humanoid robots to our world can give us numerous benefits, be it navigating through uneven and hazardous terrain. That is a thing that robots with wheels have a real hard time doing, or just by serving as assistive robots. And although they can give us numerous benefits, this problem is extremely hard to is a extremely hard problem to tackle. It involves very complex, high-dimensional, nonlinear physics, and are inherently unstable. And given that, there's still a lot of room for improvement in this field. Also, there are plenty of ways to teach a humanoid robot how to walk. Reinforcement learning has seen lots of success in other fields, but they rely heavily on simulated environments and are thus really computationally costly to train. Also, they tend to be hard to translate from simulated robots to real robots due to the well-known sim to real gap. And they tend to also lead to sometimes some unnatural behaviors, as they also rely on very arbitrary heuristics to converge. Particularly for the problem of humanoid robots, model predictive controllers has seen a lot of success, but again, they are really computationally costly because they involve using a online iterative optimization solver to converge. And thus they tend to be impractical to use both for simulated robots and even more for real robots. So based on that, the objective of this work is to develop a fast algorithm that can be used in real time that will mimic the behavior of a model predictive controller, inheriting all of its strengths and robustness, and doing that through imitation learning of the MPC using a neural network. We expect this algorithm to be able to follow any reference to its center of mass speed, to walk stable, while being able to withstand random disturbances to its center of mass speed, such as a push. So now I'll go over the dynamics of humanoid robots and the stability criteria that we used. So stability is one of the main points of humanoid robot walking. The robot must be able to walk stable in order not to fall. The most widely used stability criteria is the zero moment point proposed by Vukobratovic and Borovat in 2004. It can be seen as the dynamic equivalent of the center of mass projection, but for dynamic bodies. It is the point on the ground where the reaction force acting on the robot's feet cancel out every other force and momentum acting on the robot, so it is stable. We can see here in figure 5 on a 2D simplified view of the ZMP that we can generalize every other force acting on the robot's body to be summed up to a tuple of one force and one momentum acting on the robot's ankle, here designated by force Fa and momentum Ma. Also, there is the force of gravity acting on the robot's feet, designated by force Fg. So then the zero moment point will be this point P, where the reaction force acting on the robot's feet, here force Fp, will cancel out the forces and momentum acting on the robot. So there is nothing acting on it, so it is stable. The ZMP, the robot will then be stable if the zero moment point is inside the support polygon, that is the convex hole formed by the robot's feet that is in contact with the ground. Here in figure 6, we can see again a 2D illustration of the ZMP related to the stability. In the first figure here on the left, the robot is in double support. So its support polygon is delimited by this red line here, formed by the area between both feet. In this situation, the ZMP is inside the support polygon, so the robot is stable. On the second illustration on the right, the robot is in single support, so its support polygon is only his support foot. And in this situation, the ZMP is outside the support polygon, and then the robot is unstable because it is moving. It is important to notice, though, that although the ZMP guarantees stability for the robot, it can sometimes be a very over-restrictive criteria, because if the ZMP is outside the support polygon, it does not mean that the robot will immediately lose control and fall. It can recover stability with future steps, and this point will be more important further into the presentation. As for the dynamics, the complete dynamics of humanoid robots is very complex. As I said, it involves high-dimensional nonlinear physics, and because of that, researchers usually opt for a simplified dynamics. Kajita in 2001 proposed a method called linear inverted pendulum model that reduces the dynamics to one simple linear differential equation. It does that by dismembering the Newton-Euler equation for rigid bodies and asserting 4 assumptions. First, the robot must be walking on a plane so that the gravity only points on its z direction. Then the robot's center of mass height must be constant. The ZMP must always be inside the support polygon for it to coincide with center of pressure, and the angular momentum rate can be neglected. If we respect those 4 assumptions, we can then derive the following LIPM equations here in equations 1 and 2 for x and y axis, where the center of mass, where the ZMP depends only on the center of mass position and acceleration. From that, we can generate a center of mass trajectory that will guide the ZMP to always stay inside the support polygon, and then the walking is stable. Okay, now for the theoretical background on imitation learning. Imitation learning is a method of machine learning where an agent learns by observing and mimicking an expert. It does that because the expert generates pairs of states and actions that will guide the learning of the agent. Imitation learning can be divided into 2 basic categories: behavior cloning and inverse reinforcement learning. Behavior cloning is the simplest form of imitation learning. In this method, the agent learns the policy, that is, each action to take in each state, directly from observing the expert. It operates as kind of a supervised learning in machine learning, and more importantly, it does not need to interact with the environment. That is important because interacting with the environment with a non-optimal policy while the robot is still training can be dangerous if we're using real robots in the real world, and can be also very computationally costly if we're using simulations, for example. Accessing the simulation every time to iterate upon it can be very computationally costly. On the other hand, inverse reinforcement learning is a method where the agent learns the reward function from the expert by observing the expert, and then uses this optimized reward function within the environment to learn and optimize the policy using standard reinforcement learning. We can see it as the agent not trying to just mimic the actions of the expert that it took in each state, but rather trying to find the reason why the expert took those actions. It tends to work well for problems where the reward function is the best way to describe the problem. We can think of a game of chess, for example, where there are an infinite number of states. It seems more reasonable to learn the reward function rather than learning each action to take in each of the infinite states of the game. In our case, we chose the simplicity of behavior cloning. It is well known that it may not be sufficient for more complex tasks, but for our case, where we had a large and diverse data set that was going to be presented further into the presentation, and where we also didn't have any problem with censoring, as the data set was generated in a simulation where we had access to every state at every time. And we also didn't face the problem of correspondence, because both our expert and our agent were basically the same robot using the different controllers. So for our case, behavior cloning was more than enough to teach to mimic the NPC. I'll go now over the literature review on humanoid robot walking and imitation learning. The preview control of the zero moment point dates back to the seminal paper of Kajita in 2003. Weber in 2006 then extended his work to use a MPC to better account for restrictions of the support polygon and better adapt to disturbances. And although up to this point this made for a good controller, it is important for the robot to adapt to disturbance that it can adapt its footstep position and duration to overcome the disturbances. Haired et al. In 2010 then further extended this work to automatically decide on footstep placements. In 2014, Ibanez et al. Then further improved the work of Haired by using a mixed integer quadratic programming formulation to also decide on the footstep durations, which was later proved by Fang that was of substantial importance to overcome disturbances. Moreover, the work of Maximo and Afonso, here present, further contributes to this field by developing a model predictive controller that also uses mixed integer quadratic programming to automatically decide on footstep positions, durations, and rotations, while accounting for constraints of joint limitations, acceleration limits, and such. And because of that, it is the method that it is chosen as the expert for our agent. In 1999, Cavagnari et al. Showed that although methods that plan ahead of time using receding horizons, such as the MPC, can achieve great performance, it tends to be impractical to use in real time. He then proposes a neural network to approximate the MPC offline, then to be used online. Shen et al. In 2018 also proposed a deep neural network formulation to approximate the optimal control law of a explicit MPC. So we can see from this literature review that recent studies have showed success in using neural networks to approximate MPCs. Moreover, in his work, Karius et al. Proposes a imitational learning approach to mimic an MPC, which he calls MPCNet, to copy the behavior of a quadruped robot. In this work, he uses the Hamiltonian law to explicitly employ the overall control law and constraints into the network. Later, Heskey et al. In 2021 extended his work to use a single policy, a single MPC, to control multiple gates of the same robot. Although many pieces of work have been conducted in this field, to the best of our knowledge, we don't know of another work that uses imitation learning to mimic an MPC for humanoid robot walking. And that is where this work tries to explore. Now I'll go over the methodology used to develop this work, both on the MPC that was used as the expert, mainly developed by Marcos and Alfonso, and also the imitation learning methodology used to develop the imitation learning controller itself. Because of that, I will be briefer on the first, because the focus of the work is on the imitation learning, and I'm going to focus more on the latter. So optimizing an MPC, it is done using a mixed integer quadratic formulation to optimize a set of decision variables under a quadratic cost function and subjected to a set of inequality that sets the constraints. The decision variables are the jerks of the robot, the positions and rotation of the string input, and a binary variable that says how many, which time step is active on each footstep. The rest are auxiliary variables that help shape the quadratic mixed integer quadratic programming. The cost function involves 5 parts. The first and red one is used to penalize the jerk usage, that is to avoid unnecessary use of energy. The green part is to penalize the MPC not following the reference velocity. The blue part is to penalize it not keeping the ZMP on the center of the support foot. The orange part is to penalize it not following the footstep duration reference. And lastly, this purple part is to penalize it not following the footstep rotation reference. Each of these is then weighted by its own positive constraint. Also, the MPC has a set of constraints that help shape the problem. There are sets of constraints to help the binary and auxiliary variables, but we are more focused here on the ones that help shape the walking problem itself. So there are constraints that limits the velocity to account the center of mass velocity to account for joint limitations. There's a constraint that limits the acceleration. There's a constraint for the footstep placement of the robot, that is to maintain a minimal distance between one another to avoid collision. And that is a constraint to avoid the ZMP leaving the support polygon to guarantee stability. To mimic this controller, we proposed a two-headed deep neural network that has both a regression end, because we have regression variables such as the jerk, and classification in a classification end. This network was then optimized using a well-known optimization tool named Optuna, and also by hand. While optimizing this network, we saw that some hyperparameters were more important than others to optimize, and that some of them could be reduced and change its values without losing performance. And because of that, and knowing that we wanted a fast algorithm because we wanted it to be used in real time, we came to the conclusion of this architecture seen here in figure 8. More details over all of the hyperparameter tuning can be seen on the full dissertation, because more here I just want to focus more on the overall architecture. To use the imitation learning controller on the robot and to be able to comprise with every other aspect of the algorithm, such as the inverse kinematics, low-level control loops, and such, we chose those as inputs and outputs for the network. It receives as inputs the position, velocity, and acceleration of the center of mass, the position and rotation of the swinging foot, the reference in velocities, and a categorical variable that says how many time steps the robot has spent in the current footstep. That is for it to follow the duration reference. As outputs, we have the jerk of the robot, the position and rotation of the swinging foot for the next time step, and a binary variable that says if the robot should or not touch the ground at the beginning of the next time step for it to change its support feet, for example. You can see that there's no variable saying which one is the support foot, the left or the right. That is because as the robot is symmetric with respect to its sagittal plane, it makes no difference for us. Its right and left side are equal. So we mirror the data when the robot was using the left foot as support foot, as if it was using the right one. That is done because with this we can reduce the dimensionality of the problem because we have one less decision variable. We also reduce the range of some variables, and we enforce symmetry because if we had both feet as support feet for the problem, the neural network learn different behaviors for each one depending of the distribution of the samples each one saw. So in this way, we enforce the symmetry that the robot will act equally on both sides. Furthermore, we also change the frame of reference from inertial to the center of the support foot. For some variables, such as positions, that means translating and rotating. For others, such as velocity and acceleration, this means just rotating. And for angles, it is more straightforward, just a subtraction. We do this because in some simulations, the frame of reference is inertial, for example, at Zibo, or in the simulation that we use to generate the dataset. And again, we want the frame of reference to be centered around the robot because that way we also reduce the range of some variables. With that in mind, we generate data set of random trajectories. A trajectory is a set of 50 time steps that follow a random reference following a uniform distribution that can be seen here in equation 11. Each of these reference is then multiplied by a binary variable that says if this direction is active or not. That is to diversify the data set for it to have references in single and multiple directions. Also, the robot has a 50% chance of suffering a random disturbance at any moment, point in time. That is also follows a uniform distribution, here denoted by equation 12. And after that, we then generate 3,000 trajectories, each with 50 time steps, resulting in 150 samples, 150,000 samples. As we exclude the unfeasible data, that is data where the model predictive controller couldn't find a solution, returning a vector of zeros, we get to around 117,000 samples. We then further divide it into 90% for training and 10% for validation. And as always, we normalize every continuous variable using a standard scalar. Okay, now for the results of this methodology. First, well, we trained the model for 95 epochs. We used a early stopping callback as a regularization method. And we also use a learning rate scheduler for it to reduce the learning rate every time the validation loss had hit a plateau. As we can see from figure 9, the model trained very well. And our strategy of starting with a higher learning rate and reducing it on strategic times was a success, because we can see here on epochs 36 and 60 that reducing the learning rate drastically improved the performance. We can also see that the model trained well and there was no overfitting, because at the end of training, both training and validation loss had stagnated. We then tested the trained model with 4 different trajectories. There was a trajectory walking forward, one rotating to the side, walking to the side, excuse me, one rotating, and one with reference in every direction, here divided into in 4 trajectories. We can see here that it's very difficult to notice any difference between the ground truth, the labels, and the output of the model in almost every the rotation, the binary variables. Only here in the last graph, you can then believe me that there are 2 overlapping curves here. But this difference is minimal. So we can say that the model had an excellent performance both in all training, validation, and test sets. But having good performance is just not enough, because that the MPC can do. We also want it to be real fast. So to assess that, we compared the computation times of both the original MPC and the imitation learning controller by running it around 10,000 times each. The imitation learning controller was ran on the embedded hardware of Chapi, while the MPC ran on a much faster and powerful desktop computer. We can see here from the histogram that is in log scale that the imitation controller was overall much faster than the MPC. More than 99% of its execution times were below 1 millisecond, while the MPC only managed 18% of the times to be below 100 milliseconds. That is the entire walking period that is allocated for the walking algorithm, that comprises of not only the controller, but also the inverse kinematics, low-level control loops, and such. So, and also we can see here that the variance in the execution times of the imitation learning is it's almost non-existent. So we can reliably expect that it will always be fast in all of its executions. On the other hand, the MPC, its execution time fluctuates depending on how many iterations the solver took to get to a solution. Overall, in average, the proposed imitation learning controller ran on a worse processor and still managed to be on average 650 times faster than the MPC. So we can say that it is feasible to be used in real time. Then we tested the algorithm in LIPM simulations. That is the same simulations that we use to generate the data set, in which we give a trajectory of the robot starts on an initial position and follows a reference on a trajectory of 50 time steps, having the possibility of suffering disturbance to the center of mass positions, velocities, excuse me, such as a push. The first experiment was for the robots to walk forward. On the left, we have the original MPC. On the right, we have the imitation learning controller. We can see here that it's very hard to notice any difference between the two gates generated. The imitation learning controller could follow the reference very well and manages this MP to always stay inside the support polygon, then being stable during all the walking. The second experiment was for the robot to rotate. And again, it is very hard to notice by eye any difference between the two behaviors. We can see that the MPC managed to stay stable and follow the reference. The green circles here denote the discrete ZMP placements in the time steps. So you can see that it is always inside the support polygon, the edge of the support polygon. The third experiment was then for it to walk forward, but receive a disturbance, a push backward. And this time we can see a little bit of discrepancy between both behaviors. On figure on the right here, we can see that the imitation learning controller placed its 50 time step on a different position as the MPC. But overall, it was still able to follow the reference and overcome the disturbance. We also can see from the green circles that in the 50 time step, it had 3 green circles. That is, it spent 3 time steps in this footstep. In the fourth, it spent 4, and in the sixth, it also spent 4, as opposed to 5 in every other footstep. That is the reference duration. So we can see that the algorithm successfully adapted its footstep placement and duration to overcome the disturbance. In the fourth simulation, it was then set to walk forward and receive a disturbance in the Y direction. Again, it is hard to notice any difference as the imitation learning controller successfully followed the reference and overcame the disturbance. This time we can see, I don't know if it's easy to see, but we can see there are 6 time steps in the fourth footstep. So this time it adapted its footstep duration to last longer to overcome the disturbance. Then we tested the controller on a realistic full body simulation on Gazebo, on our high fidelity Sharpie simulator. We do this because we want to test the entire algorithm of not only the controller, but the gravity compensation, control loops, inverse kinematics under realistic physics, reproducing the body, the robot's joints, the body, and the contact forces. The first simulation was for the robot to just walk forward. And again, we see a behavior that is as we expected. In the X and Y graph here, we can see that it followed the reference and manages to keep the ZMP always inside the support foot. On the X center of mass speed graph here, we can say that the neural network successfully predicted the actions to follow the reference. Here is saw by the red line. The reference was 0.2 meters per second, and the predicted by the neural network follow this, even though due to imperfections of the simulation and the robot balancing by changing support foot, it fluctuates around it a little bit. And then we set it to walk forward and again receive a push in the backward direction. And one more time, it is as we expected because it followed the reference and manages to adapt its footsteps to overcome the disturbance. Here in the center of mass speed for the x direction, we can see again that it was following the reference of 0.2 meters per second. Then it suffers a disturbance of negative 0.2 meters per second, going with its center of mass speed to 0, but it rapidly recovers it and regains control of following the reference here seen from the red line. Although those simulations show how good the controller is, we must also see how good it is to overcoming strong disturbances as strong as the MPC could. So we then compare the disturbance margins by on both a theoretical manner on the LIPM simulations and on a practical manner on Gazebo. We did that by changing the angle in which the disturbance was given and seeing how great of disturbance the robot, the controller, could withstand. Here in the theoretical comparison, we can see that the MPC on the left again and the imitation learning controller on the right, that the imitation controller could withstand almost as strong as disturbance as the MPC. The blue part here denotes the areas in which the controllers could withstand the disturbance, and the red part denotes where it fell. We can see here that only on the 60-degree angle it could not bear as strong as a disturbance as the MPC, but overall it was very similar. But the problem with a theoretical comparison is that, as we said earlier, the ZMP is very over-restrictive, and we saw from the simulations that sometimes the imitation learning controller would receive a strong disturbance and it would not manage to place the ZMP inside the support polygon, but it would be off by just a little bit, and possibly and most likely the robot would not fall. So we chose to compare the disturbance margins in Gazebo, where we again change the angle of the disturbance and give it a push until it really fell. We can see from the practical disturbance margins that this time the imitation learning on the right did even better than the expert, the MPC. It could withstand stronger disturbances than the MPC. This is because while the MPC, when it fails to have a solution, it returns a vector of zeros. The imitation learning controller tried to come up with a solution that made sense and could be good, and sometimes it did manage to make the robot not fall. We can see this as the MPC kind of simulating or trying to relax the constraints, trying to come up with something that made sense, even though it wasn't the right answer. So we can see from these simulations that not only the imitation learning controller had a good performance, it also generalizes well for situations in which it never saw as the unfeasible data from the MPC. Finally, we tested the algorithm on the real robot Chappie. Here we can see snapshots of the controller being used to make it walk. We did that by mounting a camera on top of the field it would walk on and placing markers on its head to track its position and rotation at every time. The first simulation was it again to walk forward, and we can see here from the first figure that it did it successfully. The blue line is the robot's X position over time, and the red dotted line is the reference. We can see that walking forward, it manages to follow the reference. The other graphs show us what we expected as well. In the rotating, we can see that it just fluctuates a little bit because of the robot tilting by changing its support foot. And in the Y position, even though it did not follow directly a straight line because of, again, problems with real-world simulations, we can see that it again also tilted by changing spot foot as we expected. The second experiment was for the robot to walk forward and then suddenly stop and start rotating. From the first figure, we can see that on the time it was set to walk forward, it again followed the reference with success. And also when it was set to start rotating, it also followed the reference here in the robot's theta rotation over time. Again, the blue line indicates the robot's rotation, and the red line is the reference. So from these results, we can conclude that the MPC, the imitation learning controller, was able to successfully mimic the MPC, being able to follow any reference stably and to withstand to strong disturbances, sometimes stronger than the MPC could. And it did that by running 650 times faster than its counterpart, being then easily able to be ran on real time on a real robot. For lines of future work, we can try to use dataset aggregation to teach the model in situations where the MPC return unfeasible solutions. We can also further improve controllers to try to improve the walking algorithm, the walking controller itself, without having to worry about a computational time, as it can then be mimicked by the method proposed here. And finally, we can explore with more complex methods of imitation learning, such as generative adversarial imitation learning. And to finish, I want to thank my advisors, Marcos and Afonso, for their guidance and support throughout my master's. I want to thank the It Androids team, in special the Humanoids category, for the development of Shapi and letting me use it on my research. Lastly, I want to thank the National Council for Scientific and Technological Development for the funding of my research. And this is it. Thank you.
Thank you.
I want to just finish by showing the videos of the robot walking, if I may.
Of course.
Okay. Can you see the video?
Yes, we can.
Okay. So this is the robot Shapi being the imitation learning controller being able to be ran on real time on the real robot, just walking forward on a uneven grass field. Here is a video of it being used on a simulated Shapi on gazebo on different experiments. First, just walking forward, then walking forward and receiving a backward push. Lastly, rotating and receiving a side push. And finally, I want to show a video of the imitation learning controller receiving and overcoming stronger disturbances in which the MPC would fall. Here, unfortunately, in the simulation, when the MPC would fall, it returns a vector of zeros, so it just stops the simulation, but it serves as an illustration. First, a side push, a strong side push. We can see here that the MPC could not find a solution. It stopped the simulation while the imitation learning controller could receive the push and not fall. And walking forward and receiving a side push, we can see the same behavior. And that was it. Thank you.
Thank you very much, Vitor, for your presentation. Okay, so we start the session with questions and comments on your work. I'll use the alphabetical order, so I'll call Professor Nicola first. And I thank and welcome you on behalf of our master program in ITA. Thank you. Feel invited to start.
Thank you. Okay, so first of all, very nice presentation.
Thank you.
I think that the idea was very interesting because the mixed integer paradigm is very interesting in that it lets us model very, very diverse range of situations, and it's very unfortunate that it's usually too slow to be run in real time. So this is a very, in my opinion, it's a very useful application of this whole idea. So I would like to ask you a couple of questions. The first one is if you could comment on the difference that you see in between learning the MPC like you did, as opposed to learning the whole control of the robot. So because I see two possibilities when one is called upon doing imitation learning on this kind of system. You could, on one, you could learn the MPC and keep the kinematic controller as is. So
Yes.
the kinematic controller would track the trajectory that are given by the MPC or by the neural network that you constructed. Or you could just set the neural network to imitate the whole ensemble of the MPC and the kinematic controller. So 2 questions on this. Do you think it would be more difficult or easier to do either one of those? And do you think it would either one of those would perform better or worse?
Okay. I think learning the MPC would be easier for 2 main reasons. First, the variables, for example, the decision variables, there are less decision variables. You have to have an output of network that chooses, as we saw, just 6 decision variables. When you are learning the whole thing without having inverse kinematics, for example, in the background, you have to learn, for example, every joint position. So you augment the dimension of the problem. So it becomes harder for the neural network to learn. But it could work. And the second point is when we learn the MPC directly, we are already leveraging the power of well-established algorithms such as inverse kinematics and low-level control loops such as gravity compensation. So we are using a lot of things that already run in real time and are well-established. They work well. We don't want to get rid of those. So by learning the MPC, we have a easier problem for it to learn, so it can theoretically learn better, and we can achieve possibly a better performance by keeping parts of the algorithm that work really well.
Yeah, okay, makes sense. I agree with your interpretation. So I would like to understand a little bit better how the disturbances that you applied when generating the data set. So something that I didn't understand, maybe it was in the thesis, but maybe I missed it, is there were both trajectories without disturbances and trajectories with disturbances.
Yes.
And the ones that had disturbances, could they have more than one disturbance?
Okay. In this final work, we had only one disturbance. So when we start a trajectory, the disturbance point in time that we will suffer the disturbance, the magnitude of the disturbance and the reference velocity were already set. So we say, this trajectory will be following this reference and suffering this disturbance in this point in time. So we had 50% of our trajectories without disturbances and 50 with disturbances. And those that had disturbances only had one disturbance per trajectory. We tried to generate data sets. We experiment with a lot of data sets, to be honest. And amongst them was data sets in which the robot would suffer multiple disturbances. Suffer one, then suffer another. But this kind of data set overall generated a worse behavior. I cannot explicitly say the reason, but I think it is because it made it very unstable. So the network tried to learn too much to situations of disturbance and situations in which the robot would rarely find itself in, and did not learn very well only following reference, for example.
Yeah. And I was also thinking about different kinds of disturbance. I mean, I will mention them and you could comment on this and maybe tell me if you tried it or had an idea of trying it or not. So the first thing that came to mind was maybe persistent disturbances. So, for example, not impulsive disturbances, but something that could be represented, for example, by the robot walking on a slope. That would be some kind of disturbance that it's always there. And or it could represent, for example, the robot has something in hand, and that's also some kind of persistent disturbance. And the other kind of disturbance that comes to mind is model disturbance. So, for example, you have parameters in the equations that you use in the MPC. In particular, the first that comes to mind is the constant in the equation of the linear pendulum. So another approach for generating a more diverse data set would be to generate trajectories that use slightly different parameters. For example, the constant of the pendulum could be different. Did you think about this thing, or did you limit intentionally the work to data set that had simple disturbance because it gave better results?
Okay, very interesting. I don't think those are very interesting kind of disturbances, and they can potentially improve the performance by generating data set more diverse, for sure. We chose a disturbance on the center of mass speed because the purpose here was not just to develop an algorithm, but also to compare it with the model predictive controller that was developed by Marcos and Rubens. So in their work, they chose a disturbance on the center of mass speed as an impulse, and I kept it because I wanted to compare how good the imitation learning controller would be compared to the original FTC of their work. But I do agree with you that multiple types of disturbance can be experimented with and potentially can improve the performance of the network. Yes.
Okay. Could you give me a general idea on of how long did the training take? Like, both in terms of how long did it take to you to make all the decisions that led to the final version of the scheme, and the final effort in training the final network? How long?
Okay. Well, the first part, and how long did it take me to come up with this final final arrangement, I can say a lot. More than I have more than 20 gigabytes of saved models, tested models here. So it took a lot because there are so many things that we can change. We can change the parameters of the network. We can change how we train it. We can change, especially the data set. In more normal machine learning problems, the data set is with us ahead of time. We have this data set, and we want to work on it. But in my situation, I had to generate the data set during my research, and how to do it was also a very interesting part. As I said, we can the number of samples of the data set, for example, is something that I change overall a lot of times, because we tend to think that the more data, the better. But sometimes the more data, it just leads to a longer training time without improving performance. So the number of trajectories, the margins, upper lower bound of the references, for example, the choice of having references in single directions was something that I came up with along the way, because I was seeing that when I was setting the robot on just by setting the reference a random, it would never have, for example, a reference only on X. So when we try to make it run forward, it would not just run forward. It would try to not run on a straight line, because it had never seen it before. So those little tuning took a lot of time. And for the training of the network itself, well, using a modern GPU, it doesn't have to be a top-notch GPU. My personal dedicated GPU on my computer, that is a RTX, it can train the network on the full data set on under 10 minutes.
I see. So one question I wanted to ask was, do you think that it's necessary for the data to be structured as trajectories? Because being that you want to learn from state action pairs, another option would be to simply just sample the state and to use a data set that is, you just use a sample state.
Yes.
I believe there's some reason why this wouldn't be better, but maybe you know something.
Okay, that is something that we did test with, and we tested by just start the robot in this position and see what the result of the MPC would be. The problem was doing that, the robot became really unstable. It didn't learn how to walk properly. It would do very unnatural movements, and there's a paper in the literature review on the full paper that shows that learning trajectories for imitation learning is usually better than just learning state action pairs. In a hypercube, we just sample random states and actions, and we learn upon that. It is generally worse. It's proven to be generally worse than learning full trajectories, because I don't have the full insight on that, but it tends to work better. Yes.
Yeah, I suppose that, and I think you mentioned this is because essentially you want to have more samples of the kind of states that you will need more, which are
Yes.
around
Data just by itself is not always good. I mean, having data that the robot will face most of the time tend to lead it to learn a better gate.
I will ask one final question and then pass over to the other members. You mentioned a little bit how you could improve on this, starting from this framework that you developed, how you would improve it. For example, you mentioned doing inverse reinforcement learning, I believe. How would you, what would the most promising direction for improvement be if you wanted to use this algorithm as a basis, for example, for improving the performance, like using robot data, for example, data coming from the real robot itself?
Okay. I think overall the most promising is GALE, that is generative adversarial imitation learning, because from the papers that we saw, it has the power of overcoming the performance of the expert. Behavior cloning is generally bound to be just as good as the expert is. It is not what we saw here from the disturbance margins, but it is just is not the rule. Generally, behavior cloning is bound to be just as good as the expert is, and that limits us to the power of the NPC that we are using as the expert. So I see the most promising line of work being generative adversarial neural networks, generative adversarial imitation learning. Sorry, because it has the potential of being better than the expert. But that would mean changing. Gale is a very different method from behavior cloning. It must use a simulation. So it means changing the overall structure that we used here in this work. So I think one possible line of work for improving it by keeping the structure as is Dagger, the data set aggregation, because we saw from the disturbance margins that the network generalized well for situations in which it had never seen before, such as when it was given a very strong disturbance where the NPC could not overcome. But we can use data set aggregation to further improve upon this, because it is a method used to get solutions to when the neural network drifts from situations in which it saw to situations it never saw. It tends to have an error that drifts away and tends to have an exploding error, for example. It was not a particular problem here, but I think using data set aggregation could further improve upon the performance.
Okay. I maybe I used a little bit of the less of the time that I had in my disposal, but I think this is all the questions that I would like to ask for now.
All right. Thank you, Nicola.
And thank you very much for your contribution. Now I'd like to invite Professor Olivier, and I'd like to thank and welcome in name of our program too. Thank you very much. I don't think we can hear you for some reason.
Yeah, we cannot hear you.
No, we still don't hear.
Hello?
Hello.
You can hear me?
Yeah, okay, now I hear you.
Okay.
Yeah.
Okay. Sorry about that. Many thanks, Carlos, for your invitation. I'm very happy to attend this defense. And at first, congratulations for your presentation. It was
Thank
very
you.
clear and very interesting, very pleasant. And also congratulations for the document. The document was very well written. It is clear, and it shows the range of your knowledge, which is large. I mean, from the modeling and to learning. Congratulations for that.
Thanks.
Okay, so maybe a few questions. I have some question in the document. For example, first, it doesn't concern really the imitation learning, but in the modeling part, you talk about the cost function. The cost function which is used in the MIQP.
Yes.
Is on page 42. Well, of course, this cost function is a kind of compromise in between some parameters, well, like the duration of steps and so on. Did you? So there is a kind of arbitrary choice. I mean, in the choice of these parameters, alpha, beta, gamma, and delta. And so two questions: did you play with this parameter a bit to evaluate? I mean, the quality of the trajectories. And the second one is I mean this. Would you have remarked some impact on the quality of learning in this parameter? For instance, maybe the size of the jerk could make the trajectory more violent or this kind of stuff, and maybe some harder to learn. I don't know. So yeah.
Okay.
First question.
Yes. Okay. For the first question, no, I did not play with the parameters for the cost function. This part was mainly developed by the work of Máximo and Rui. So I kind of took for granted that they had done a great job of optimizing the model predictive controller. So I just took the best results that they got from their paper and used it as the expert. These constants here, what I can say is that the last two constants for the duration and rotation references, the one that weights the most in the cost function to guide the robot to always follow a reference of 5 time steps of duration and always have the right rotation, I'd say. Because, for example, the ZMP is always already on the constraints. So if the ZMP left the spot polygon, the constraint would be violated, and then the robot will the MPC will not find a solution. So the weight for the MPC could be smaller, and that's what guide us to have the behaviors we saw, that it placed the ZMP on the edge of the support foot as opposed at the center, because the weights of the ZMP was smaller and it tended to really optimize it to have a minimal cost function as possible. So in most of the situations, we see the ZMP to be at the edge of the support foot. But overall, no, I just stuck with the parameters that Massimo and Afonso found to be the best on their paper.
Okay. Well, my remark was linked maybe toward a direction that you mentioned, maybe in your well, I can't remember, in your in the perspective. I mean, of course, you don't use a reward function in the learning, but if for some other method in learning, you could learn reward. You could have to deal with a reward function, and this kind of cost function. I mean, cost function, reward function, they are kind of similarity. So it would be in the perspective to add an algorithm which used reward function with a new reward function, seeing that you use a cost function which has some arbitrary would be good, or I don't know, completely naive. It's the question. I don't have any idea. But
okay, you say if we're using, for example, inverse reinforcement learning, where we learn the reward function. Yeah. Okay. Yeah. In this case, we would be learning the cost function that is basically the same as the reward function, right? So yeah, in this case, I think it would be more viable to play with the parameters. But I don't think I don't see a reason why changing the weights, for example, or changing the cost function would impact on the ability of the network to learn. I mean, it doesn't. I don't think it would work that way. I think independently of which was the weights for every part of the cost function, it would I think it would learn the same. Yes, but I think only experiment to say for sure. Yes.
I have a more trivial question. When you compare, when you evaluate the cost of, I mean, in terms of computation of the MPC, how much step do you take? And question is, how well, are there minimal number of steps to take, or you don't know, maybe?
You say when I evaluate how long the MPC took to.
Yeah. Saying that it is not embeddable. Of course, it's not embeddable, but
You say the number of footsteps, the number of the prediction horizon.
Yeah. What is the minimum of computation steps?
Okay.
Well, steps, not computation steps.
Yeah. In this, when we did this experiments regarding how long it took to compute, it had 3 entire footsteps in the prediction horizon. So each footstep takes around 5 time steps. So
yeah, okay.
It would predict 3 future footsteps.
Okay. So it was by curiosity. I have maybe a question regarding the data generation. Let me just take. In the page 51 of your document, well, there is a table of parameters for the simulation.
Mm-hmm.
Again, there are a lot of parameters.
Yes.
How to deal with that? I mean, you put them by hand, of course. I guess. How to fix them? Have you got a method, or?
You say how I got these parameters for the
Yeah,
simulations?
exactly.
Okay.
Yeah.
Okay. These parameters are almost exactly as the parameters that Marcus and Rubens used in their in their paper. Some of them is based on, I mean, fine tuning as the, for example, foot length, foot width is to comprise with the robot's actual foot length and width, for example. The acceleration and speed limits, I think it's fine tuning as well. Finding the best behavior and limiting for the joint actuations.
Okay.
The time step I set as the same as the walking algorithm that we used on the Shapi at the moment. He used this parameter of time step. So I just wanted to maintain the same to compare the walking that we have nowadays outside of the MP and the one I was proposing. And the other one regarding the controller itself, again, I just took for granted. I just followed what Marcos and Rubens had optimized.
Okay. I would have a question also about the scene to reel. So you explain in your document and in your talk also that you experiment the algorithm on the Chappie.
Yes.
And so the output of the algorithm is a control of the COM, right?
I'm sorry?
The output of the algorithm is the final output is a control of the center of mass.
Yes.
Right. And so, well, in the context of RoboCup, that I love actually.
Yeah. I've been there in 2018, Canada. I participated.
Ah, yeah. The robots are quite, kind of low-cost robots. It's well, what I mean is that you cannot trust really in motors. You cannot trust really in the controller of motors. And so when you have when you are given with an order and jerk like that, what do? You, to come in finally in a control, I guess in position control of each servo motors.
Okay, the algorithm it stipulates that we can control the jerk, but in fact we cannot control directly the jerk. So what we do is we derive the jerk to get to more usable acceleration, for example, and then we interpolate this value to act on the robot, and we pass this to the inverse kinematics algorithm to then act on the joints. So we don't act on the jerk directly. We do manipulation with it to, yeah.
You mean that you act on the position in fine of the center of mass?
Yes.
Yeah. Okay. And then you do inverse kinematics, and then you get the what sensor have you in the Chappie?
I'm sorry?
What sensors have you in the Chappie?
The full sense.
Do you sense? I guess you have the position of motors. These are, I can see, dynamic cell motors, or?
Yeah, they are torque motors. They are by torque.
You mean you have a control by torque? No.
I think that is. I'm not sure. I don't know if Marcus can explain better, but I think they are controlled by torque.
No, Olivier is right. They are dynamic cell servo motors.
Oh.
So they are position servos. Yeah.
Okay.
Yeah. So Giudice didn't work with those parts. He's just using the controllers we have for RoboCup.
Yeah, the controller, the dynamic cell.
Okay.
Yeah. You're right.
Yeah. So you come with a position order that you send from the inverse kinematic, from the position that of the COM that you have. So position order in the motors. From my experience, well, my question first is, have you got measured, sampled the real position of the motors? So you send orders, but are you sure that the motors are following this order? And in which square?
Okay. Yeah. Oh, yeah. I might be wrong with that one again, but I don't think they are censoring in the position of the motors. And one problem again that we had of using the Chappie on the real robot is that it cannot sense the disturbances automatically. So that's why we explored more experiments with the simulated robot, and we used on the real Sharpie just to show it runs on the embedded hardware of a real robot in real time, and it manages to follow references and all of that. But for the motors, I don't think there's a censoring of the position of the motors. But again, I don't have much in-depth knowledge on the construction of the robot,
No,
and I
okay,
think
okay, of course.
maybe Marcos and Rubens can further clarify this.
But when you make it work like that, of course, I mean, even without any perturbation, I
Yes.
think that in your video, I mean, probably the motors are very far from the orders. I mean, by experience.
Yeah, the problem,
Not,
for example, in the simulation that we did on Sharpie is that I did it some days after the team had come back from a competition, Latin American robot competition. So it was hard to calibrate the robot. It had just came back from a competition, and it was all uncalibrated. I tried to further calibrate it, so it was hard to fully leverage the power of the imitation learning controller because the robot itself was not fully calibrated. That's why, for example, we can see in the graphs it doesn't follow a straight line. The field that we were using, it was kind of uneven as well. So yeah, that was that.
Okay. Is there an IMU in the Sharpie that you use or not at all?
That is, yes.
And you use it to get the position of the center of mass?
Yes, I think they do. Yeah, the positions of the robot, center of mass and stuff. Yeah.
Okay. Maybe another last question. When you, I mean, not related to the Centauri. So you have a neural network to imitate the MPC. Would it be interesting for you to use it to measure the robustness of the command relatively to, I don't know, perturbation?
I'm sorry, could you repeat? To measure?
I mean, to use the neural network, maybe by differentiating it, to measure the robustness of the command regarding a perturbation, or I don't know. It's very open, but
you
to get a measure of the, you know what I mean, to get a measure of robustness of the controller.
I don't know if I'm getting you. Say using the neural network, for example, to have as input, for example, the disturbance. I'm not sure if I get what you're saying.
For example, you have a disturbance, so you have a family of disturbance, and you.
Okay.
I'm in some mean to some extent to get a measure of the robustness of of the controller.
You say, for example, as we have the reference as input, also have a disturbance as input.
Yeah.
Yeah, I mean the disturbance is already explicitly not implicitly described in the center of mass velocity. So I'm sure that if we had put the disturbance as input, for example, for the network, it would probably perform at least just as good as it did here, because it would have one more input explicitly of the disturbance. But I think the problem with this is that we would be limiting the neural network robustness to how good our measurement of the disturbance would be. It all depends on how good we can measure the disturbance. As always, in a simulation, is really easy to measure the disturbance because we explicitly program it, right? But for real robots, I don't think would be very easy to measure, for example, impulse
No, no.
disturbances.
I was thinking about simulation. I was not thinking at all
Okay,
to
okay.
real robot.
Yeah, in
But for
simulations,
example,
it would be
it could
easier.
be, yeah, and maybe this kind of stuff could be used to determine some trajectory or some base position. I mean, more
Yes, of
stable
course.
than others. I don't know. What do you think?
Yeah, I think if we could explicitly employ the disturbance in the input of the network, I don't see a reason why that would deteriorate our performance. I can only see it being or just as good or even better than the performance we had here, because we have the disturbance implicitly employed, right, in the center of mass position. But if we had an input of explicitly the disturbance, I have all the reasons to believe that it would increase the performance. Yes.
Okay. Well, I don't have any other question. Thanks a lot. Thanks for your answers.
Well, I thank you for participating. Thanks.
And thank you very much for your contributions. I think it's now time for my questions. I think. Okay. First of all, I'd like to thank Vitor and Massimo and Rubens for inviting me to appreciate those work. I mean, appreciate because it's very good work. It's
Thank you.
very meaningful. It's the continuation of Massimo's and Rubens' work, and you bringing it to the practice to make it work in real robots. What was difficult before. I'm very happy to see this. Okay, I have some small things I found. First of all, you work with jerk. It made me scared a little. It's very noisy thing. A jerk in the mathematical formulation, you're smoothing the jerk. You're forcing the jerk to be minimal. But do you implement the jerk as a signal? It's an output signal, electrical signal that represents the jerk.
No, we don't act on the jerk explicitly. For in the algorithm, we assume that we can act on the jerk, but in reality, we take the jerk and we derive it to get to center of mass position, for example. So we don't act on the jerk itself. Yes.
Great. Okay, I will have a question about the model. If I change parameters of the robot, and do I have to train another MPC in order to train the neural network, or is we are able to adjust a trained network for new parameters?
I mean, the MPC, I don't completely get what you say. Training the MPC is not trainable, right? So you get an MPC. You asking if we change the parameters of the MPC and want to copy with the same network, if it would work?
No, I mean, if I change the robot,
Okay.
the length of the leg, something
Okay.
like this, do I have to recompute the MPC in order to train the network, or are you able to adjust to the new situation?
Well, I think you would have to generate a new MPC and new trajectories, because that neural network is bound to that specific robot. I mean, I cannot say. It depends on the parameters you change. If you, for example, change the size of the robot's feet or some minor parameters, it might still work. But to get the best performance, you'd have to generate new trajectories and retrain the network. Yes.
Okay. Yeah, it can be some for future work.
Yeah.
I think I'm trying to spot some things for.
Sure.
Yeah. Do you test the neural network for constraint violations or only?
Not explicitly. You mean, for example, acceleration limits and velocity limits? No, we don't test for constraint violations. The only one that we really accounted for was the ZMP placement. We tested it that it was always inside the support polygon. We want to maintain stability. And but as we can see, the disturbance margins, they don't explicitly show that, but I try to make that clear in the text that the network, it simulates kind of a constraint relaxation. When we gave a strong disturbance, that the MPC would not be able to overcome. For example, in controllers, we can relax the constraints, right, to adjust for situations in which there's no feasible solution. And the behavior you can see from the network is that it tries to do the same. When we put it in a situation where the MPC would not have a solution, it tries to kind of relax these constraints. So, for example, it places its MP a little bit outside the support polygon, but maybe it would have a acceleration that is greater than the limit. But I see it as a good thing. I mean, it's not hard to limit them explicitly in code. So if the neural network has this ability to relax the constraints, and we can then further, oh no, this constraint I don't want to be relaxed. For example, acceleration limit is this explicitly. It is easy to code, right? So I see it as a good thing.
Good. Yeah, because the question, because the neural network doesn't know the constraints, it has to learn.
Yeah, it doesn't know. Yeah.
Okay. And I think it's a final question. I'll mix two questions into one thing. Yeah, you have when you train the neural network, you have a test set and a validation set. I didn't understand it. Well, what is your validation set?
Okay, so we generated these 3,000 trajectories, 150,000 samples. Actually, 117 because it's infeasible. But we then randomize it and divide out. There's 90% for training. There's 9% for validation. The difference is that we tune the parameters with the validation set, and we exclude a blind set just for testing. When we finish tuning the parameters and all of the stuff, that, for example, Optuna uses the validation set to tune the parameters, and the training is just for training. But we don't want to use the test set for it because that would be biased. We will be biasing our experiment to conform with the test set. So the test set is blind. We only use it after we had finished the training and tuning the parameters in order not to bias. We can see in the real world, putting it to test without managing to change anything, it would perform great. Yes.
I'm not sure it's all written in the thesis, but I think it's very important.
Okay.
Check.
Okay, I'll have this annotated. Thank you.
Sorry for trying to find a weak spot.
No, it's okay. It's okay. It's very
I'm not your enemy. Okay. Sorry.
It's very welcoming having this kind of commented.
Yes, it was really nice to see your work.
Thank you.
It's very well written and very meaningful, I think. And thank you again. And I think it's time to for the. I think I'll call Marcos Massimo first, or Rubens. You choose who wants to start first.
Okay, so there is no difference from me. Maybe Rubens can start first, then I'll be last.
Yeah, my pleasure. So I was co-advisor, so first of all, I would like to thank everyone here today for their insights, for sharing their insights with us, because I was taking notes here and I got really good ideas for future work from you guys. So thank you very much. I also would like to just state that it has been a pleasure to work with Vitor and Professor Massimo in this line of research. I've been working with Professor Massimo now for a couple of years, and it has always been very interesting for me. And having Vitor join the team, and he did excellent work, in my opinion. He was also very diligent with the results and not satisfied with intermediate quality results. He really struggled to get the best out of it. So I myself am pretty satisfied with the results. Some small comments as to the ideas, some of the ideas that I took notes of from Dr. Nicola. Yes, I think we got a very good idea for future work, which is to maybe just, there are two alternatives. One could just try to include different disturbances such as persistent disturbances or even parameter variations in the data set and learn directly with these parameter variations, which should in a more heuristic way make the controller robuster. Or now, since we do not have a constraint on time anymore, because we just try to keep our MPC simpler because of time constraints, we could go for a really robust MPC with robustness to disturbances, which can be done quite easily, and also robustness to parameter variation. And that requires a bit more computation time. But since we are going to just run this for creating a data set and then learn from it, it would be robust per imitation and not really robust riskily, but it would learn from a robust MPC. So I kind of loved this idea. I will for certain discuss with Professor Massimo to explore it in future work. And now Professor Foster also gave me a really good idea that I was taking a note of, which is with MPC, can we really parameterize some of the stuff and really have those parameters as variables in the dataset generation? Well, I was thinking this is just the first draft of an idea. It's really not very, just wrote it down. But yes, if you use this quadratic programming based MPC, for instance, we know it's mathematically proven in a paper in Automatica from Morari and Porad that the solution is piecewise affine in the state. So you can actually do what they call multiparametric MPC. The solution of this QP is a region, is a polytopic region of validity because the constraints make it polytopic. And you have a finite number of polytopes inside. In each of these polytopes, the optimal control is affine in the state. And then you can predetermine the matrices for the affine combination and do it parametrically in the state. But then you can also include other parameters, such as, for instance, in my opinion, acceleration and velocity limits, because they appear on the right-hand side of the inequalities. It's not difficult to let them as parameters in your MPC and try to solve it. You have kind of a parameter, and then you just specify the value of the parameter, which is kind of a slice in a polyhedron in dimensional space, and you have the data set. So maybe we could try something like it that does a slice and then does a new data set. If the learning is then also linear in that, maybe we could even just learn with the parameter itself as an input for the network. So this is a great idea. I think we might also have to explore this in the future. This should be very interesting also. So again, and Olivier gave us also a lot of practical issues that we then address and could address better. But for the practical issues, then I have to go back and give Marcus Massimo the word because he's the expert at this point. So thank you again. And it was very, very important for us to have this kind of insightful discussion.
Massimo.
Okay, so thank you all. First of all, thank you all for participating in the committee here. Thanks, Professor Foster, Dr. Nicola, and Professor Olivier for giving very good ideas here that we certainly want to work later on them. And also, I want to thank Professor Rubens again for the partnership. So he was my PhD advisor, and we still work together. And he's the expert here about mixed integer and MPC, and it has always been a pleasure to work with him. And also, I want to congratulate Giudice on the good work. So when we started this work, I remember that I thought this was going to take like 2 or 3 months. I remember that I told Giudice that, and we had a call, I think, from Advanced Robotics at that time about MPC, something learning and MPC, and said, "Oh, we're just going to send to that call." That was 3 months when he entered the master's program, and at the end, it took many more months than we expected at first. So it was much harder than we thought at first. And as Giudice already said here, most of the things were related to the data set, how you sample the data set. Yeah, should we just sample at random given a hypercube in the state space? Or should we use trajectories? And which kind of trajectories are we going to consider? What is the bias that we put in the dataset collection to find states that are really relevant for this task. So this was not easy. There was a lot of experimentation for that. So this is the main reason it took so much time, and also the network to tune the neural network to consider the right features. It takes a lot of experimentation and fine tuning to find the solution we have now. Of course, it's a good solution, but it took a long time for that. And the interesting part is also that we have an experimental work. So Giudice not only so most of the works related to machine learning, they just get the data set and then they train on data set and then they show some metrics saying, okay, my neural network is good. I have a low mean squared error and I have good plots here about learning. And the nice thing about the Giudice's work is that we also discovered that maybe having uh, a good metrics on terms of the imitation learning does not generalize completely to the real robot. So actually, we also had many trial and error and go and come back related to fine tuning the neural network and then deploying the neural network on the real robot or in simulation and seeing if that neural network is going to work well on the real task. So there is also this difference between training the neural network for copying the data set and making it work on the robot. So we say that training the neural network, given that data set, is like a surrogate task, but then we have the real task that we have to try, and to be able to make this deploy was something that was not easy. And as Nicola was saying, I also think that so the work is working well, but the best things about the idea, so the proof of concept of this work, where now we can have a very uh, computational costly algorithm using MPC that use mixed integer, for example, or another kind of techniques that are very slow to compute and very costly, then you can just imitate that to a neural network and run it into like 1 millisecond. So this allows us to have much more powerful techniques that we are able to run on real time. So I think this is the biggest contribution, not only copying the particular controller we have here. And also say that Giudice has finished his master thesis, the last part of the work while working, which is another challenge. So he's now at Petrobras, and I congratulate him for that. And he was able to finish his master thesis while working on Petrobras. So about the comments, I just pick some of them. So Professor Rubens has already talked about the idea that Nicola brought to us about having other kind of disturbance. I also found that very interesting and can give us many different directions for future work. But I think Rubens has already commented on that very well. So I will go to some comments from Olivier. So Olivier asked about the parameters for the simulation. So as you just said sometimes, so main configuration parts of his work are related to the work we already have, and the parameters, they are historically based on the work we have for RoboCup and for the Sharp robot. So many of those parameters were tuned by hand in some previous work, and we didn't try to change them here. But of course, you can maybe make the performance of the MPC better just by changing those parameters. And I'm not going to say that they are optimal. Of course, probably they're not. There are just some parameters that we, by experience, know that work well on the real robot. About sensing the position on the motors, actually, we are not able to do that right now on a robot. I know that the robots from Roban can do that, but we have a problem on the bandwidth on the bus that the electrical bus that we use to communicate between the servos of the robot, and the bus is not fast enough for us to read all the servos in the control sample, in the sample time of the controller. So actually we are not doing that in the experiments that you just show here. Of course, we do that in simulation. So in Gazebo, you are reading all the servos, all the position of the joints, but in estimating the center of mass position and another things. But on the real robot, the walking is working just like a walking pattern generator. So it's just generating a pattern for the center of mass, and you are trying to follow this pattern in an open loop fashion. But of course, we have an IMU, as Oliver asked about, and this IMU is used to estimate the orientation of the torso, and we have a closed loop for the orientation of the torso, so we just have a closed loop to make the robot upright, but we don't have information about the center of mass position because we're not able to read the joints in time to have a closed loop for the center of mass. Then, as Olivier told, actually we have a lot of mismatch between the commanded position for the center of mass and the one that the robot is executing. But even with all this mismatch, the robot is still able.
Hello?
Yeah, I think Marcus froze. We have a problem with his network. Yeah.
I'm writing here for.
Yeah, okay.
Yes, it's our network in IT.
Yeah, I think Ruben's frozen as well, right? Rubens, are you there? Yeah, I think both of them froze. Yeah.
Yeah, not in ITA, so
Yeah, I can see.
work there's some problems. And my neighbors here playing music. I try a phone call. Not even the cell phone is working. So
But you know how the
I think Rubens is back.
yeah, the recording will be because Marcus was the one recording it. So I don't know.
It keeps on recording, I guess,
Okay.
because for me, it just asked me if I still want to.
Okay.
Yeah.
Okay.
So sorry about that. We had a connection issue here at the institute. So our offices are just a couple of dozen meters away. So if I fall, Marcus falls also.
Yeah.
Can you go get Marcos there? Okay.
Yeah, he's back. He's back. Yeah.
Yeah. All right.
Sorry, the network here is at ITA, so professional about that. Our network is not the best. Okay, I think I was just talking about why you use the jerk. So this is actually something that is like historical in humanoid walking that come from Kajita, which is a very famous researcher in the field. So, but in the end, we don't use the jerk. Actually, we integrate the jerk and then we use position to control the robot. Yeah, it's just a mathematical trick to write the dynamical system. So that's all. In the end, I want to thank again everyone for participating here and dedicating their time to evaluate the work. Thank you.
And thank you very much. I have to open for the audience. If someone wants to say something, feel free, feel invited. Se alguém quiser falar em português também, vai ficar gravado, vai ficar registrado, né? Então, fique à vontade. Yeah. Well, I don't think anyone wants to say something, but okay. Okay. Now, the committee will need either go to a separate room or people, the audience, and Vitor leaves this room with, I think the second is better.
Okay.
Is it okay?
Yeah, sure.
So I ask you.
So I stop recording, so we don't
Yeah.
record the
We need
private
to stop
session.
recording. Yeah.
Yeah.